Today we're going to wrap up a lot of things we've been learning over the past couple weeks and tie them into horizontal position of something. In this case, we're just going to call the random thing a particle. Could be anything. Could be a molecule, could be an ant, could be a person, could be a vehicle, a bicycle. So we are going to call it PVA. We're going to talk about the position, velocity, and acceleration functions and what information we get out of them. But like I said, it's also the horizontal motion of something. Right. Here are the variables we're dealing with. T is going to be time, of course. And then we are going to talk about the x of t. Well, the x of t, we want to talk about the horizontal positioning. So horizontal is your x-axis, right? Vertical would be going up and down. So with respect to the x-axis, if something is moving horizontally, well, it's moving with respect to time, right? Where is it 1, 2, 3 seconds after it started moving? How about 25 seconds after it was moving? So it's in a different horizontal position. From there, if we take the derivative of the position function, from here on in, just so it's been said, the horizontal position we're going to refer to as the position. Okay, we're not referring to the y. We're not going up in the air yet. Just talking about horizontal. So the velocity of that position function is going to be the derivative. And then the acceleration function, which is the rate of change of the rate of change. Think about the velocity. If you're dealing with a horizontal position of miles, and then your velocity is miles per hour, well, then you can tell the rate of change. But what's the rate of change of your rate of change? Well, that's your acceleration. Think about you hit your accelerator in the car. Well, you're changing your miles per hour to a new miles per hour. It's the rate of change of your rate of change. That's the derivative of velocity, which is the second derivative of the position function. Speed, you're going to also be asked to find speed of something. Well, speed is just the absolute value of velocity. We'll think about this. So if I ask you what's the velocity at time 3, and you plug in a 3 and you find the velocity is, well, let's just stick with miles per hour, 55 miles per hour. Well, now think about this. If I'm going down the thruway and I put it in reverse and I do 55 miles per hour in the other direction, well, what's my speed? My speed is 55 miles per hour. It's in a negative direction. So we think of it as the absolute value of velocity. This gives a nice little summary of what's happening at different locations, different points and all, even intervals. But so we're dealing with motion now, right? We're dealing with a position of something in motion. So we have over time. So now we have a horizontal x-axis that we're going to actually graph vertically, because what happens now is time is our independent variable, right? So if you notice here, over time, 1 Mississippi, 2 Mississippi, we want to know where the position is, okay? So here's what we're looking. So that position would be your x of t value. Sorry about that. So position, would be your x of t, right? The x value, which is, don't forget, your horizontal position. Well, let's see what it says. So your position, displacement. So let me talk about displacement for a moment over time versus time. Displacement is nothing more than the change in position over time, right? And the change in position, well, if that's your x, well, that's the change in x values. And, well, the change in x values over an interval would be delta x. And if you're starting from a to b, well, then the change in x would be basically the numerator of your slope function, right? Except in this case, what would your slope look like? Well, the slope of your change in position over time would be the change in your x values. I meant a. Over the time frame, which is b minus a. Okay, same concept, you're just finding the change in x over the time. And if that's the slope of the x position, well, that's the derivative. That right there would be your velocity function. Okay, so if you're dealing with graphs, you can think of that when asked to find certain things given straight lines. It's when you're dealing with curvature. Okay, once things are not straight lines, but once you have curvature, well, then your velocity is changing at different rates. That's when we introduce calculus. But before we talk about that, let's just think about what these graphs tell us. So if over time your position doesn't change, well, that just means if you stay here, you don't move. So you're basically staying idle. So this right here is no movement, as it says right here. The object is at rest. It's stopped. Okay. The 3 dots just means therefore, if you're not sure. So basically your slope is 0 if you have a straight line, and that is also the velocity. Don't forget the velocity is the derivative of the position function. So this is where your velocities would look like 0. Okay, those are, think of mins and maxes. When you have uphill slopes, well, uphill slopes means that your velocity is positive. If it's a straight line, it's constant. And just, if it isn't constant, well, it could still be, velocity is still positive. It's just sometimes you have different rates of change of your velocity. It might be curving that way or this way. We'll get to those in a graph momentarily. But if you have negative slopes, if they're going downhill, well, same thing. Your velocity is negative, right? You know that uphill is positive, downhill is negative. If you're curving, well, that just means that you have some sort of acceleration. Okay, you're either decelerating or accelerating, depending if your rate of change is increasing as time goes by, or if it is decreasing as time goes by. All right, I'll make this stuff smaller, and there's my displacement, and here's that graph if you're still looking at that. Focus your attention here for a moment. Remember, if you need to pause and copy stuff down, get caught up, please. Here, just when you're starting to put all these little pieces to the graph, well, now as time goes by, your x motion, well, that just means you're not moving horizontally. And then, well, if you have positive velocity means that you're moving in the positive direction. And then if you have negative velocity, it means you're going downhill. That means you're going towards the negative direction of the x values as time goes by. Now let's put all these ideas together in this graph right here. I don't need this anymore. This is an x horizontal positioning graph that has the t-axis as your horizontal, because now that's your independent variable. And now your x positioning is changing with respect to what time it is, right? If I start here at 0, well, here, before I do that, let me bring this up. And let's put this, well, here, that's right there. Actually, I want to do this. I want it to be as big as we can. Now for horizontal positioning, I chose our particle, or our object in this case, to be a Segway. This thing is really cool. You sit in it and it's a Segway. Isn't that cool? I need to get myself one. Anywho, that's really lazy. So let's do this. We start here at 0. And I'm going horizontally, but with respect to time. Here I start at 0, I'm at 0 in my Segway. And now this is saying to the right, 1 Mississippi, 2 Mississippi. Well, this is the positive direction, so horizontally I'm going to the right. So at 1 second, So I do this, 1 Mississippi, and I am right here. So after 1 Mississippi, I should be at a horizontal positioning of +6. And then for that amount of time, I just stay there, la-di-da-di-da. I'm not moving. I have no motion, no horizontal motion. But then I start velocity decreasing, which means my movement or my velocity starts going down towards the negative direction. Dun, 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 dun. And then at 3 seconds, notice where I am. After 3 seconds, I'm back horizontally where I started at 0. And then I start going towards the left here, the negative direction. So time goes by, 1 Mississippi, and then at 4, where am I? I'm over here. At 4 seconds go by, and my horizontal positioning is at -4. After that, I think you get the idea, whatever time that is. We start traveling back up towards the 0 point, and if that is 5.5, if that is 5.5, that would be where we are at 0 again. Now displacement, like we just said, is the change in position over time. So if you look at this, my horizontal positioning, well, if I did the entire direction over, 5.5, let's say, seconds, my displacement is 0 because my change in position, I'm right back where I started. But let's say we just said, what is your displacement at time 4? All right, well, at time 4, remember here, we started at an x value of 0, and now our x value over here is -4, which means we did what? We have a displacement of -4 units, which translates into moving towards the left of the graph 4 units. Now let's tie in the velocity graph. Oh, first, if you're dealing with a graph with straight lines, well, you have constant velocity, constant rate of changes, so you can just use the slope formula. The only difference is the same concept with calculus. You use calculus when you have curves. So let's just draw this, hang on, let me do a little bit better job. So let's draw a green graph here where we have a slope of 0 or a max right there, and it curves, and let's say right there is let's say that's a point of inflection. Okay, I'm going to draw a point of inflection right there. and then we're coming down, and let's say we have a minimum right there at 4, at t equals 4. So it's the same exact concept with straight lines, just with, derivatives. Well, derivatives are the slopes of the tangent line. So you notice how you're increasing at a different rate, then you're decreasing at a different rate, then you're changing the curvature of your graph, et cetera, et cetera. You have a min here, you have a max here, and you notice how you have zero slopes. Okay, well, now to tie in a velocity graph. This would be v of t, which is also the derivative graph, right? Let's think about what we have here. So over here is where you have derivatives that are positive, which means your velocity values are, I'm sorry, that's supposed to be a plus sign, positive, okay? Which means somewhere over here you are in the somewhere over here you are in the positive direction until, well, now up here, right here, we have a velocity at time, whatever that is, that equals 0, right? We have a horizontal line, that's the slope of 0, which means down here at this time point right here we have a 0 value on the velocity slope. Now down here we start going downhill, right? So this entire interval going down to 4, let's put a 4 right here. Well, that interval right here, your velocities are decreasing. And when you have a velocity decreasing, you have negative slopes going downhill. So on your graph, that would look like this. After that, you have negative, remember, these are your negative values, these are your positive values, right? That's where you have a 0. So you have negative values all the way up here until you get up to time 4, because at time 4, I meant to draw this, you have a velocity function with a value of 0 at time 4, because that's a horizontal slope. So you have a 0 value here. And then notice after that, your slope values continue to increase. So on the velocity graph, you would now have positive velocity values. So if I said, what's the velocity at time 2? Well, the velocity at time 2, because I have a negative slope, it's decreasing. But if I was looking at this graph and I said, what's the velocity at 2? Well, the velocity at 2, here's 2. Well, 2 is a negative number, whatever the negative velocity is. Okay, negative velocity means it's decreasing. So anything down here, we are decreasing. Anything up here, we are increasing. And over here, this interval, we are also increasing because we have positive velocities. Regarding this point of inflection here, I pointed out, well, remember what that is. The point of inflection is where your second derivative values are 0. And, well, then that means, so here your second derivative values are your acceleration function. So your acceleration, well, here when you're concave down, your acceleration is negative. And over here, when your second derivative values, in this case, is your acceleration function, when those are positive, well, you're curving upward, you're concave up. So if you're changing concavity, this is where your acceleration values would be 0. In this case, let's call that right there 2.5. Okay, so at 2.5, we have a acceleration value of 0. Now, if we said your acceleration is the derivative of velocity, I didn't draw this exactly correct, but right here, that means that I would have a 0 value on the slope, a 0 slope value, because this would be the derivative of velocity equaling 0, the slope values of velocity, which we just said was the acceleration function, which means we have a 0 value there. Here we have something moving along the x-axis, so horizontally, where the velocity given across our interval between 0 and 18, oh, by the way, everything with time frames, we can't go back in time yet, so we'll always be starting our time intervals at 0, or in this case, greater than 0. We have the v of t function here, so before I talk about the inflection points, let me talk about what this v of t, these are where your positive v of t values are, and this is where your negative v of t values are. So if this is where your v of t values are positive, that is where your original function is increasing. I meant right, increasing, INC. Over here, well, if this is where your v of t values are negative in this that region right there, so basically between 11 and 16, right in that region, you have velocity values that are negative. And that means on your original function, which is x of t, that indicates you are going downhill, you are decreasing. And anywhere where your velocity values are 0, well, remember what that indicates on your original function, your position function. That means that you have 0 slopes, and that means you are at rest. Onward with our example. So we have the v of t graph we are looking at. The inflection points on this graph are marked with green circles. Find all the values of x where the particle is at rest. X values that are at rest. X values that are at rest. X values that are at rest. They are trying to throw you off by giving you the points of inflection. Remember what graph you're looking at. If you want to know where your X values are at rest, we want to know where the velocities are 0. And we are looking at the velocity graph, which means we have a 0 value here, and a 0 value here, and a 0 value here. So I'm going to say at time 3, that is 11, and then at 16. Those are the 3 time frames where our X value, the particle, is at rest. Let's take a look at another one. Particle is moving along the x-axis, and the velocity, again, we have the velocity function. Be mindful of that. Here is our positive velocity and our negative velocity. We know the inflection points. All right, remember the last one they threw us off with the inflection points. Maybe this will help. Let's see what we're given, what we have to find. Find all x, same question, different graph. They're trying to throw you off with those inflection points. We are looking at velocities of 0, right? If you want to know where the x values are at rest, well, that means you want to know where the slope of the tangent lines of x are 0. That's your velocity function. And that's what we are looking at, the velocity graph. So just like before, we want to know, now just because those are points of inflection, that's irrelevant, all right? The answer here is, well, we have one at time equals 3, one at time equals 9, 12, and 16. What if the question on this graph asked us, what's the velocity? Is the velocity increasing? Is the velocity increasing or decreasing at, let's say, time equals 11 and time equals 14? Just because that happens to have a 0 slope on it, that means nothing for us in this question. That just means that at time 11, you have a positive velocity, which means you are increasing, all right? And then, well, if you look at 14, at time 14, I don't care about the slope of the tangent line there. I just want to know what's the velocity. You have negative velocity values, which means at time 14, you're decreasing. Just so it's been said, this positive slope here, well, remember, if you're looking at the velocity graph, those derivatives or slopes of tangent lines are the derivatives, right? And well, what did I say at 14? So let's plug in what is the slope of the tangent line at 14? Well, I don't know the number, but I know it's a positive value, which would indicate that the acceleration at 14 is positive. So even though I don't have the acceleration graph, I can look at the slopes and determine acceleration values if I needed to. What if we're not looking at a graph? What if we are just given a function and said, well, let's see what this one says. A particle moves along the x-axis along time is 0 or greater than 0, and its position is given by this horizontal position function, t squared, you can read it. Determine all the values of t where the particle is at rest. Now, this is the same question as before, just we don't have a graph. Well, remember what we're looking for. If it says we want to know what t values the particle is at rest, well, the x value is that's the position function, which means the derivative of the position function when it equals 0, that is when our particle is at rest. All right, well, that's when the velocity function is 0. So let's see what we get. Let's start by taking the derivative. And that's going to be 3t squared, plus minus 27. If we want to know when it's at rest, we want to know when the derivative equals 0. And remember, the derivative equaling 0 is your velocity value equaling 0. I'm going to take out a common factor because that is going to make this easier to factor. That's a 9. And I'm going to divide both sides by 3, so I think you know that's just going to go away because 0 divided by 3 is 0. That makes it easier to factor out. These factors look like t plus 9 and t minus 1. Did I do that right? Positive 8. Yep. And you're going to get a t equals negative 9 and a t equals 1. Since our interval is dealing when time is 0 or positive, we don't deal with -9. We have a t-value of 1. Our particle is at rest at time 1. Next, we have a particle that is moving along the x-axis horizontally. Time is greater than or equal to 0. And here's our position function. Determine the acceleration at particle 2. Well, the acceleration we said was the second derivative, so that's going to look a little something like this. To get to the velocity function, that's the first derivative. That would be the velocity function right here, minus 24. So if it asks me what's the velocity at time, well, here, let's just do it right now. What if they ask you what is the velocity at time 2? Well, that right there would look like this. You do, well, 2 times 2 is 4. Plus 6, the t is 2, and then you have negative 24. So the velocity at time 2 would be 12 plus 12 minus 24. Oh, ironically, that comes out to be 0. You'd have a 0 slope there. But it does not ask us for the velocity. It asks us for the acceleration. So to get to the acceleration function, don't forget, this is the first derivative. This is the second derivative. Let's continue. 6t plus 6. All right. We want to know what is the acceleration at time 2. So you plug in a 2 into the acceleration function, and that's going to give us 12, but that's going to give us 18. Think about this. I can even tell you more. I also know that at time 2, this is concave up because the acceleration is the second derivative, and when your second derivatives are positive, you know it's concave up. Just want to tie it into something we've already learned. Next, we have a particle moving along, and again, if I'm going too fast, stop, pause, and copy. Rewind if you need to. A particle moves along the x-axis. Time is greater than or equal to 0. Here's our position function. Let's determine if the particle is moving to the right or to the left at time 5. While x is the position function, the velocity is the movement of your position function. So if you are moving to the right, that means you will have a positive velocity, and if you are moving to the left, you have a negative velocity. Let's take the derivative. The derivative is your velocity function, and that is negative 2t minus 8. The negative 23 goes away. And this is as simple as saying, well, what's the velocity at time 5? All right, well, that's going to be this. That's going to be a 5. That's a parenthesis 5, 8. That's a negative 10. Looks like we have a velocity of negative 18. So remember what negative 18 indicates. We are moving to the left. So since this thing equals negative 18 and it is negative, the particle is moving to the left. Let's talk about speed now. So what if they asked you, a particle moves along the x-axis, you know the interval, we have an x position function is this. They want to know the speed of the particle at t equals 2. Well, remember that the speed is the absolute value of velocity, which means we want to know what's the absolute velocity, the absolute value of velocity at time 2. The velocity function is the first derivative, and this is what we get. All we need to do is plug in what is v of time 2. So that's going to be 4 minus 10, that's a negative 6. So we get ourselves the absolute value of negative 6, which means it's a positive 6. There is your correct answer. Now, what about the speed when you start changing speeds? Well, you can increase your speed, right? You could decrease your speed. And, well, let's see what this one asks. Oh, first, I got to show you this. When speed is increasing, well, you're speeding up, right? And when you have a decreasing speed, you are slowing down. Think about it when you're driving the car. Here's how we're going to calculate when your speed is increasing. Well, that is when your v of t and your a of t both have the same sign at some specific t value. So if you plug in a time value, say 3, and you get a velocity of negative and an acceleration of negative, well, that's the same sign. That means you're speeding up. So you're looking for a positive, positive, or you're looking for a negative, negative. You're slowing down when your velocity and your acceleration functions at some time value have opposite signs. So you're either going to have a v of t with positive and an a of t of negative, or the other way around, okay? But if they have opposite signs, you can tell me it's slowing down at that time or over an interval. Let's spend a moment and look at this graph before I jump into the next question. Say we have a curve right here, and this is our x of t, our position function, and I'm going to say that we have a point of inflection right there, and I'm going to tell you right here is where you have, well, this is where your velocity would be 0, and here, this interval is where your velocities are positive. And over here, your velocities are negative throughout this entire interval between here and here, before you have a velocity value that's 0 again, and 0 is where it changes back to positive. So you have positive velocity values here. Regarding curvature, well, if there's my point of inflection, right here is where it's curving downward, which means I have a of t values that are negative in this region. Here's where I have an a of t that would be a 0 value, point of inflection. And then after that, you see how it's curving upward. That means that we have second derivative or acceleration values that are positive. Let's take a random point. For argument's sake, let's say this value right here is where t equals 1. This is my t-axis, okay? And if I meant to write 1 there. So if I said, at time 1, is it speeding or slowing, is speeding up or slowing down? Well, let's see what we got here. We said over here, that is at t equals 1, we have a velocity at 1, which is positive, right? It's going uphill, the slope. And the acceleration at 1, well, it's curving downward, which means it's negative, which means it is slowing down at time 1. Let's pick another random point. Say I pick right here, and we'll call that time 3. All right, well, at time equals 3, what do we get? Well, I want to know what's the velocity at 3 and what's the acceleration at 3. The velocity at 3 would be the slope of the tangent line. The slope of the tangent line is going downhill. That's a negative slope. But the acceleration is the curvature. And if you notice, during time 3, our acceleration is curving upward. It's after the point of inflection, which means it's positive. And when they are opposite, it is slowing down. I guess I should do one that's speeding up. Let's do one that's speeding up. Let's continue and say right here is time 5, and I want to know at time 5, is our particle speeding up or slowing down? Well, what we have to do is we have to see at time equals 5, what is the velocity at 5 and what is the acceleration at 5. If you look at the velocity is the slope of the tangent line, and that is a positive slope during time 5. But the acceleration, well, the acceleration happens to have the same value here. Notice how it's curving upward, which means the second derivative is also positive. And when you have the same signs, that is when your particle is speeding up. So it would be speeding up at time 5. Now let's do a problem. A particle moves along the x-axis, so the time greater than or equal to 0 is given by this position function, and we want to know, is the particle speeding up or slowing down at time 7? Well, we kind of just showed you graphically. Well, now let's do it algebraically. So down here, I'll just bring it down here. We have the velocity function. Well, let's take the derivative. That's going to be 2t plus 5. There's the position. There's your velocity. And we want to know what's the velocity at time 7. Going to be 19, right? 14 plus 5. And now we also have to do, let me change the color, we have to do the acceleration function. So a of t, well, that's just 2. What does that mean? Well, that means, so that just means what, regardless of what time frame I plug in, well, it's always a positive 2. This right here is positive 19, and this is positive 2. Because they have the same sign, we can say that at time 7, our particle is speeding up. Next example. We have a particle. It is moving along the x-axis. Same type of question. We want to know if it's speeding up or slowing down at time 3 now. Well, let's do the same thing as we did before. Oh, I forgot. I didn't plug in all the answers here on the last one. I'll do it for this example, and you can see what the answer should look like. Let's take the velocity function. The velocity function comes out to be negative 3t squared plus 4t plus 32. We are going to need to know what the velocity at time 3 is, so I'm going to plug it in right now. That's a 3 squared is a 9. This is 4 times 3 plus 32. We have ourselves negative 27 plus 12 plus 32, and that right there is going to give us a positive 17. All right, now for the acceleration. I'll do it over here in blue. The acceleration function, well, if we're taking the derivative of that, it would become negative 6t plus 4. And we want to know what is the acceleration at time 3. That's going to be negative 6 times 3. That's going to be negative 18 plus 4. That's a negative 14. Notice here how they have opposite signs. If they have opposite signs, like we said before, it is slowing down at this point. How would I plug this into this delta math example? Well, since v of 3, we just did v of 3 is a positive 17, and a of 3 is a negative 14, the particle is slowing down. Why? Because velocity and acceleration have opposite signs. And that's how you would populate those answers.